Hi, I'll be continuing my lecture of chapter 6 into 6.4, which is the refrigerators and heat pump. Okay, so the transfers of heat from a low temperature medium to a high temperature medium requires special devices called the refrigerator. So this refrigerator here is actually referring to just make your life easy, the fridge at home, yeah, your house fridge. Okay, so refrigerators like heat engines are cyclic devices. Like what I say, it goes through a cycle and then comes back to the original, goes through the cycle, comes back to the original. Okay, the working fluid is the refrigerant itself. Yeah, and the most frequently used refrigeration cycle is the vapor compression refrigeration cycle. It's like your household refrigerator. Okay, let me just explain here. Okay, the place your fridge becomes colder, which means the heat from the colder area goes to the evaporator. So the colder place becomes colder, whereas the warmer place becomes warmer because the heat from the condenser expels out to the kitchen air itself, which is warm. Okay, so this is actually defying the second law of thermodynamics. Yeah, like what we said in the last lesson, that heat from the hot area goes to the cold area, from the hot goes to the cold. But in this case it works because why? It has external work net which is coming from outside, which is the electricity itself. Yeah, that's the reason why it can actually defy the normal law. Yeah, so this device is actually making the colder area cold and releasing the heat to the warmer area. Yeah, so a fridge at home, you have the evaporator, which you cannot see. This is actually in your freezer itself. The old freezer, they have coils. Yeah, but the newer fridge, everything is concealed, you can't see that. It goes to the compressor and the back of the fridge. This part is the back of the fridge. Yeah, the back of the fridge is always warm. Yeah, and then it goes to the expansion valve where your pressure from 800 kilopascal drops to 120 kilopascal, and also the temperature actually also drops from 30 degrees to negative 25. So this is your house refrigerator. Yeah, okay. Now COP, coefficient of performance. Okay. It's something like your efficiency, but then they don't use the word efficiency for heat pumps and also refrigerator. They use coefficient of performance. Coefficient of performance is the desired output. So in a fridge at home, what is your desired output? It will be your QL, isn't it? Because you want to cool the colder place. Whereas what is the required input? That would be your electricity that went into the fridge. Yeah. So the COPR, R is for refrigerator, yeah, will be 1 over QH over QL minus 1. Okay, so that is the COP for a refrigerator. And if you see this diagram here, can you see it taking out heat from the colder area, going through the process of refrigeration cycle and release the heat to the warmer area. Okay, next would be heat pumps. Now what is your heat pump? Heat pump is, Malaysia, we don't use heat pump, yeah, because our weather is warm enough. Heat pump is mostly used in a country where we have winter. Yeah, your heater, your indoor house heater, yeah, you don't have in Malaysia. We only use aircon in Malaysia, right? Okay, how does a heat pump work? Heat pump takes heat from a cold environment and pushes into the warm environment. Can you see that or not? The QH actually is being pushed to 20 degrees, which is warmer. Okay, and also once again it defies the second law, because by second law it says it has certain energy by right. It's the other way around, right? But this works here because there is an input. There is an input, which is your electricity itself. Now for heat pump, the coefficient of performance would be the desired output. So what's the desired output of your heat pump? You want to heat up your environment, right? So it will be QH divided by work net in. Yeah, so the summary of the formula will be 1 over 1 minus QL over QH. It's a bit different from the other one, yeah, because the desired output here will be QL, whereas for this fella, the desired output is QH. Okay, so let's solve a question. Yeah, Before that, let's go through some. Most heat pumps in operation today have seasonal average COP of 2 to 3. Most existing heat pumps are use the cool air outside, as a source of heat for the during the winter. In cold climates, the efficiency drop considered because when the temperature are below the freezing point. In such geothermal ground source heat pump that uses the ground as the heat source can be used. Such heat pumps are more expensive to install, but the operating cost is cheaper. Air conditioner are basically refrigerators whose refrigerated space in the room or building instead of food compartment. So air conditioner is similar to your refrigerator. The concept is similar to the refrigerator. So the COP of a refrigerator decreases with the decreasing refrigeration cycle itself. Therefore, it's not economical to refrigerate to a lower temperature than it is required. That's the reason why you should set the desired temperature in your refrigerator, not too cold. You're wasting electricity. Okay. Now let's look at Clausius statement. Clausius statement. What did Clausius say? It is impossible to construct a device that operates in a cycle and produces no effect other than transfer of heat from a lower temperature body to a higher temperature body. Okay. Example. Without electricity or without a work net in, you cannot take heat from a cold environment and push it to the warmer environment. You cannot. You need something which comes from outside. Okay, that's what he's trying to say. It states the refrigerator cannot operate unless its compressor is driven by an external power. That's your electricity. This way, no net on the surroundings involves the consumption of some energy in the form of work in addition to the transfer of heat from a colder body to a warmer one. To date, no experiment has been conducted that contradicts the second law, and this should be taken as a sufficient proof of validity. Okay, so if you want to define the second law, you must have some work net in, either form of electricity or some other form of energy. So the equivalence of these two statements, Kelvin-Planck and Clausius statement. So you can actually generate this kind of diagram. You can just have a look at it. So any device that violates Kelvin-Planck also violates the Clausius statement, and vice versa. Okay, so this I'll go into the next lecture. Now let's just discuss a question here. One of the example I've just extracted out from the textbook. Heat rejection by a refrigerator. So this is your house refrigerator. Okay, the compartment is actually at 4 degrees, and then we have QL360 work net, which is your electricity going in at 2 kilowatt, and then you have heat that's being released. So maintain at 4 degrees, removing heat at 360, and its required power input is 2 kilowatt. So what is the COP of the refrigerator? So COP of refrigerator is QL, desired output, divided by work net in, which is in this case is 3. B, the rate of heat rejection to the room that houses the refrigerator. So how do you calculate that? The rate at which the heat is rejected to the room that houses the refrigerator is determined by the conservation of energy in relation to the cyclic device itself, which is your QH equals to QL plus work net in. So how much work net in just now? 2 kilowatt. But kilowatts unit you have to change here because this is kilojoule over minute. So you need to change your kilowatt into kilojoule per minute. This is the conversion. So once you're converted, the total value is 480. So with that, we have ended this part of the